Hello, and welcome. Tonight, we're going on a journey together, a journey unlike any other. You don't need to do anything but listen. Let your body sink into comfort. Let your breathing slow. And allow yourself to drift along with the words. We're going to explore a question that humans have asked since we first looked up at the night sky. How big is our universe? But this isn't just about numbers and distances. It's about perspective. It's about understanding our place in something so vast, so incomprehensibly large, that even trying to grasp it can bring a strange sense of peace. When you realize how enormous everything truly is, your daily worries begin to feel lighter, smaller, more manageable. So close your eyes if you'd like. Picture yourself floating in the darkness of space, safely cocooned, looking out at the cosmos. We'll start small, right here at home, and slowly, very slowly we'll expand outward, layer by layer, until we reach the very edges of what we can observe, and perhaps even beyond. Take a deep breath. Let it out slowly. We have all the time in the world, or rather, all the time in the universe. Let's begin. We start here, on Earth, our pale blue dot, suspended in space. If you were to walk around the equator of our planet, you'd travel about 40,000 kilometers. That's roughly the distance you'd cover if you walked for an entire year without stopping. But let's leave Earth for a moment. Let's travel to our nearest celestial neighbor, the Moon. The Moon sits approximately 384,000 kilometers away from us. That might sound like a tremendous distance, and in human terms, it is. The Apollo astronauts took 3 days to make this journey. 3 days of traveling at thousands of kilometers per hour, just to reach that silvery sphere we can see with our naked eyes on a clear night. Imagine that journey now. Imagine leaving Earth's atmosphere, watching our blue planet shrink behind you, becoming smaller and smaller until it could fit in a window frame. The blackness of space surrounds you. There's no air, no sound except your own breathing and the gentle hum of your spacecraft. And then, gradually, the Moon grows larger ahead of you. Its gray, cratered surface becomes clearer with each passing hour. 3 days of travel through the void, and you arrive at a world that has watched over Earth for billions of years. But this is just the beginning. The Moon, for all its symbolic importance to us, it's practically in our backyard when we consider the true scale of space. Let's continue outward, past the Moon into the realm of our solar system, the Sun. Our star sits at the center of everything we call home. It's about 150 million kilometers from Earth, a distance we call 1 astronomical unit. Or, light from the Sun takes 8 minutes and 20 seconds to reach us. Think about that for a moment. When you feel sunshine on your face, you're feeling light that left the Sun over 8 minutes ago. Now, let's visit the other planets. Moving outward from the Sun, Mercury, the closest planet to our star, orbits at just 0.40. It's a scorched, cratered world where temperatures swing wildly between blistering heat and freezing cold. Venus, our toxic twin, sits at 0.7 AU, shrouded in thick clouds of sulfuric acid. Earth, of course, is at 1 hour perfect distance from the Sun, in what we call the habitable zone. Mars, the red planet, orbits at 1.50. It's the last of the rocky, terrestrial planets. Then comes a vast gap, the asteroid belt, and beyond it, the gas giant Jupiter, the king of planets, resides at 5.2. This massive world is so large that over 1,300 Earths could fit inside it. Yet it's still just a tiny speck when viewed from the outer solar system. Saturn, with its magnificent rings, orbits at 9.50. Light from the Sun takes over 1 hour and 20 minutes to reach Saturn's clouds. Uranus, tilted on its side, spins at 19.0 from the Sun. And Neptune, the farthest official planet, dwells in the cold darkness at 30 or 30 times Earth's distance from the Sun. Picture Neptune now, It's so far away that the sun would appear as just a very bright star in its sky, offering little warmth to this frozen blue world. A year on Neptune lasts 165 Earth years. Since its discovery in 1846, Neptune has only completed one full orbit around the Sun. But even Neptune isn't the edge of our solar system. Not by far. In 1977, humanity launched two spacecraft, Voyager 1 and Voyager 2, a grand tour of the outer planets. After visiting Jupiter and Saturn, and in Voyager 2's case, Uranus and Neptune, these twin probes continued outward. Into the darkness beyond the planets, Voyager 1 is now the most distant human-made object in existence. As of our current time, it's over 24 billion kilometers from Earth, roughly 160. At this distance, a radio signal from Voyager takes over 22 hours to reach us, traveling at the speed of light. Think about that. Even light, the fastest thing in the universe, takes nearly a full day to traverse that distance. These spacecraft are moving at about 17 kilometers per second, faster than anything else we've ever launched. And yet, at this incredible speed, Voyager 1 has been traveling for over 45 years and has only just recently crossed into interstellar space. Beyond the influence of the solar wind, the Voyagers carry golden records, phonograph records, containing sounds and images from Earth. A message in a bottle thrown into the cosmic ocean. These records will outlast our civilization, drifting silently through space for billions of years. Long after humanity has disappeared, right now. At this very moment, as you listen to these words, Voyager continues its lonely journey, moving farther from home with each passing second, sending back faint signals from the edge of our solar system's influence. But Voyager hasn't truly left our solar system yet. Not in the fullest sense, far beyond Neptune. Far beyond Pluto and the other dwarf planets of the Kuiper Belt, there exists a vast, spherical cloud of icy objects surrounding our Sun. This is the Oort cloud. Named after the Dutch astronomer Jan Oort, who first theorized its existence. The Oort cloud is staggeringly distant. It begins at about 2000 from the Sun and extends outward to perhaps 100,000. Oh, that's nearly 2 light years. Remember, a light year is the distance light travels in 1 year, about 9.5 trillion kilometers. To put this in perspective, if the Sun were the size of a grain of sand in New York City, the Oort cloud would extend past Chicago. Over 1,000 kilometers away, this cloud contains trillions of icy bodies, remnants from the early solar system. Occasionally, gravitational perturbations send one of these objects tumbling inward toward the Sun, where it becomes a long-period comet spectacular. Visitors that grace our skies once every few centuries or millennia. The Oort cloud represents the true boundary of our Sun's gravitational domain. Beyond it lies interstellar space, the vast ocean between the stars. And this is where our journey truly begins. Because everything we've discussed so far from Earth to the Moon, through all the planets, past Voyager, all the way to the Oort cloud, all of this is just our immediate neighborhood. One star's domain. Our galaxy contains 400 billion stars. Let that sink in as we prepare to venture outward, into the darkness between suns. Take a slow breath. Let your body relax even more. We're about to expand our perspective in ways that will make everything we've discussed seem incredibly small. The journey continues. Asterisk. Beyond the Oort cloud, space becomes truly empty. The vast darkness between stars is almost incomprehensible in its scale and emptiness. The nearest star to our Sun, Proxima Centauri's 4.24 light-years away. Let's pause and really understand what this means. Remember, light travels at just under 300,000 kilometers per second. That's fast enough to circle Earth's equator 7.5 times in a single second. At this speed, light reaches the Moon in 1.3 seconds. It reaches Mars in about 3 minutes when the planets are at their closest, but Proxima Centauri is so far away that even light, racing at this incredible speed, takes for years and 3 months to bridge the gap. If we could somehow travel at the speed of the Voyager spacecraft, our fastest probit would take us over 73,000 years to reach Proxima Centauri. That's longer than all of recorded human history. Proxima Centauri is part of the Alpha Centauri system, a triple star system that has fascinated astronomers and science fiction writers alike. The system contains at least 2 confirmed planets, including Proxima Centauri b, which orbits within the habitable zone of its star. Imagine standing on that world right now. If you looked up at the night sky, you would see 2 suns orbiting each other, Alpha Centauri A and B, and there, among the countless stars, you would see a familiar yellow star, unremarkable among the others. That would be our Sun, as seen from Proxima Centauri. Earth would be completely invisible, lost in the glare of our star. This is our nearest stellar neighbor, and between us and them, nothing but vacuum, radiation, and occasional atoms of hydrogen drifting in the cosmic wind. Let's take a moment to truly comprehend the light year, because it's going to be our primary unit of measurement from here on out. 1 light year is approximately 9.5 trillion kilometers. Written out, that's 9,500 billion kilometers. It's a number so large that it becomes almost meaningless in everyday terms. So, let's try to scale it differently. Imagine you could compress 1 light year into a single year of driving in a car at highway speed. You'd need to drive at 100 kilometers per hour continuously, without stopping, for over 10 million years to cover 1 light year. Or think of it this way. If the distance from Earth to the Sun hour, astronomical unit, were reduced to the size of a single inch, a light year would still be over a mile long. The universe operates on scales that our brains didn't evolve to process. We evolved to understand the distance from one tree to another, from our home to the next village. But now we're trying to grasp distances that span years of light-speed travel. Yet we must use these scales, because anything smaller becomes impossibly cumbersome when dealing with cosmic distances. Kilometers and miles lose all meaning when we venture beyond our solar system. So we measure in light years, the distance light travels in Earth's 1 revolution around the Sun. It's poetic, in a way using our own planet's journey as the basis for measuring the journeys of light across the cosmos. Between the stars lies a void unlike anything we experience in our daily lives. Space isn't just empty, it's almost perfectly empty. In interstellar space, the average density is about 1 atom per cubic centimeter. For comparison, air at sea level on Earth contains about 25 quintillion molecules in the same volume. The emptiness of space is so extreme that the best vacuums we can create in laboratories on Earth are cluttered by comparison. Yet, this void isn't completely devoid of everything. There are wisps of gas, mostly hydrogen, forming vast, diffuse clouds between the stars. There are grains of cosmic dust, tiny particles no larger than particles of smoke, drifting through the darkness. These dust grains are often the remnants of ancient stars, their atoms forged in nuclear fusion and scattered into space when those stars died. There's also light, though you might not see it with human eyes. Starlight fills the interstellar medium, a faint, pervasive glow that would only be visible if you could somehow block out the light of individual stars. There's infrared radiation from dust warmed by distant suns. There are radio waves. There's the cosmic microwave background radiation, a faint echo of the Big Bang itself, pervading all of space. And there's a magnetic field, weak but measurable, threading through the galaxy like invisible strands of silk. But mostly, there's distance. Vast, cold, empty distance. If you were floating in interstellar space, halfway between our Sun and Proxima Centauri, you would see stars in every direction, but they would all be distant points of light. The Sun would be just another star, perhaps the brightest one visible, but no longer the dominant furnace it appears from Earth. You would be truly alone in a way that's difficult to imagine, surrounded by light that has traveled for years to reach you, in a silence so complete that no sound has ever disturbed it. This is the ocean our galaxy swims in. And like an ocean, it has currents, tides pulled by gravity, regions of density and emptiness, storms of radiation from exploding stars. We tend to think of space as a void, but it's better understood as a medium incredibly thin, but not entirely nothing. It's the stage on which the cosmic drama plays out. Zoom out further now. Expand your mental map to include not just dozens or hundreds of stars, but hundreds of thousands. Our Sun resides in a small, minor feature of the Milky Way galaxy called the Orion Spur, also known as the Orion Arm. This is a minor spiral arm, perhaps more accurately, a spur connecting to major spiral arms measuring about 10,000 light-years in length and 3,500 light-years across. The Orion Spur is named after the constellation Orion, which lies in this same region of the galaxy from our perspective. This is our local galactic neighborhood, containing not just our solar system, but millions of other stars. When you look up at the night sky, almost every star you can see with the naked eye is within this same structure. The stars that form familiar constellations, Sirian the Hunter, Taurus the Bull, Gemini the Twins, are all part of our local arm of the galaxy. We're seeing the structure of our neighborhood from the inside. The Orion Spur is a busy place by cosmic standards. Stars are being born here in stellar nurseries like the Orion Nebula, vast clouds of gas and dust where gravity slowly pulls matter together until it becomes dense enough to ignite nuclear fusion. And stars are dying here too, some quietly fading away, others exploding as supernova and scattering their enriched material back into the interstellar medium, where it will eventually form new stars and planets. The Orion Spur is positioned between two major spiral arms, the Sagittarius Arm on the inner side, closer to the galactic center, and the Perseus Arm on the outer side. These major arms contain more stars, more gas, more of everything there, the main features of our galaxy's spiral structure. We're in a relatively quiet part of the galaxy, not too close to the chaotic center, where stars are packed densely together and supermassive black holes lurk. Not too far out in the sparse outer regions, where stars are rare and heavy elements needed for planets are scarce. We're in what some astronomers call the galactic habitable zone, a Goldilocks region, where conditions are just right for stable planetary systems and, perhaps, the emergence of life. But even this local structure, containing millions of stars, is just a tiny piece of something much, much larger. As we prepare to zoom out further, take a moment to let this sink in. Everything we've discussed, every star system, every light-year of space between them, exists within just one minor feature of our galaxy. The Milky Way stretches far beyond the Orion Spur, a vast island of stars that will take us much longer to cross than any distance we've covered so far. Rest now. Breathe slowly. Feel yourself floating in the darkness between the stars of the Orion Spur, surrounded by distant points of light, part of a structure so large that it would take thousands of years at light speed to traverse. We're about to go bigger still. Now we pull back even further. Imagine you could rise above the plane of the Milky Way, floating in the darkness of intergalactic space, looking down at our entire galaxy spread out before you. What you would see is breathtaking. The Milky Way is a barred spiral galaxy, a vast pinwheel of stars, gas, and dust, rotating slowly through space. From above, it would appear as a bright central bulge surrounded by elegant spiral arms that sweep outward in graceful curves. Like cream stirred into coffee, frozen in time, the galaxy is approximately 100,000 light-years in diameter. Let that distance settle in your mind. Remember, light takes for years to reach our nearest neighboring star. Now multiply that by 25,000, and you have the distance from one side of our galaxy to the other. If you could somehow travel at the speed of light, the fastest speed possible in our universe, it would take you 100,000 years to cross from one edge of the Milky Way to the other. Civilizations could rise and fall in that time. Species could evolve. Ice ages could come and go on Earth dozens of times. The galaxy is structured in several distinct parts. At the center lies the galactic bulge, a densely packed spherical region about 10,000 light-years across, glowing with the light of ancient red and yellow stars. These are old stars formed when the galaxy itself was young. Over 10 billion years ago, surrounding the bulge is the galactic disk, a flattened structure about 1,000 light-years thick, where most of the galaxy's stars reside. This is where we live, in one of the spiral arms that wind through this disk. The spiral arms themselves are regions of higher density, where gas and dust accumulate, triggering waves of star formation. They're not fixed structure. Stars don't orbit the galaxy within a single arm. Instead, the arms are like traffic jams in space, regions where stars temporarily slow down as they orbit, creating areas of higher density that appear as bright spirals when viewed from afar. There are 4 major spiral arms in the Milky Way: the Perseus arm, the Norma arm, the Scutum Centaurus arm, and the Sagittarius arm. Our little Orion spur connects the Perseus and Sagittarius arms. A minor bridge between these greater structures, beyond the visible disk, lies the galactic halo, a roughly spherical region extending perhaps 600,000 light-years from the galactic center. This halo contains globular clusters, ancient, densely packed groups of stars, each cluster containing hundreds of thousands of stars bound together by gravity. These clusters orbit the galaxy like satellites, and they're among the oldest structures in our universe, nearly as old as the cosmos itself. The halo also contains dark matter, that mysterious substance we can't see but know exists because of its gravitational effects. In fact, most of the Milky Way's mass isn't in stars or gas at all. It's in dark matter, an invisible scaffold that holds the galaxy together. This is our home galaxy, a vast island of stars adrift in the cosmic ocean, rotating majestically once every 250 million years. The Milky Way contains an estimated 400 billion stars. 400 billion. Let's try to comprehend this number. If you counted one star per second without stopping to sleep or eat, it would take you over 12,000 years to count every star in our galaxy. That's longer than all of recorded human history. If every star in the Milky Way were a grain of sand, you would have enough sand to fill all the beaches on Earth. With plenty left over, these 400 billion stars come in an incredible variety. The vast majority, about 3/4 of all stars in our galaxy, are red dwarfs. Small, cool stars with masses less than half that of our Sun. These stars are so dim that not a single red dwarf is visible to the naked eye from Earth, despite their overwhelming abundance. Yet they're the longest-lived stars in the universe. The smallest red dwarfs will burn steadily for trillions of years, far longer than the current age of the universe. Then there are stars like our Sun, yellow dwarf stars, medium-sized and medium-temperatured. These stars are relatively rare, making up perhaps 7% of all stars. They burn for about 10 billion years before exhausting their fuel. There are orange stars, cooler and smaller than our Sun, and red giant stars that have exhausted the hydrogen in their cores and swollen to enormous sizes. Some red giants are so large that if you replaced our Sun with one, its surface would extend beyond Earth's orbit. There are blue giants and supergiants, massive, hot stars that burn brilliantly but briefly. A blue supergiant might have 20 or 30 times the mass of our Sun and shine with the light of 100,000 suns. But it will exhaust its fuel in just a few million years, a cosmic eye blink, before ending its life in a spectacular supernova explosion. There are white dwarfs, the dense cooling embers of dead stars, each one packing roughly the mass of our Sun into a sphere the size of Earth. There are neutron stars, even denser still, containing more mass than our Sun, crushed into a sphere just 20 kilometers across. A teaspoon of neutron star material would weigh as much as a mountain on Earth, and there are black holes, regions of spacetime, where gravity is so intense that not even light can escape. The galaxy is dotted with stellar mass black holes, the remnants of the most massive stars, each one waiting silently in the darkness, warping space and time around itself. Each of these 400 billion stars is a sun in its own right. Many of them likely have planets. Recent discoveries suggest that planets are common, perhaps even universal, around stars. That means there could be hundreds of billions of planets in our galaxy alone. How many of those planets have liquid water? How many have atmospheres? How many have life, even simple microbial life? How many have civilizations looking up at their own night sky, wondering if they're alone? We don't know. But the numbers suggest we might have a lot of company in this galaxy. Yet for all this abundance, stars are still incredibly far apart. Remember, the distance to our nearest stellar neighbor is over 4 light years. If the galaxy were scaled down so that the distance between stars was just 1 meter, the Milky Way would still be over 10 million kilometers, cross about 25 times the distance from Earth to the Moon. Space is vast, and even in a galaxy containing hundreds of billions of stars, most of the volume is empty darkness. At the very heart of our galaxy, 26,000 light-years from Earth, lies something both fascinating and terrifying. Sagittarius, a pronounced Sagittarius, a star, a supermassive black hole. Anchoring the center of the Milky Way with its immense gravity, this black hole contains approximately 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit around the Sun. The event horizon, the boundary beyond which nothing, not even light, can escape, is about 44 million kilometers in diameter. That might sound large, but it's tiny compared to the mass involved. The density is staggering. We can't see Sagittarius A* directly, because, by definition, black holes emit no light. But we can observe the effects of its gravity on nearby stars. There are stars orbiting close to the galactic center that whip around this invisible monster at speeds of thousands of kilometers per second. By tracking these stellar orbits over many years, astronomers have been able to precisely calculate the mass and location of the black hole. One star, designated S2, orbits Sagittarius A* once every 16 years, coming within 17 light hours of the event horizon at its closest approach. During these close passes, the star experiences relativistic effects-time dilation, predicted by Einstein's theory of general relativity. Time literally moves more slowly for this star at its closest approach to the black hole. In 2019, astronomers achieved something remarkable. They captured the first image of a black hole shadow. While this image was of a different galaxy's central black hole, M87*, efforts continue to image Sagittarius A*. The challenge is that while M87* is much more massive, it's also much farther away, and Sagittarius A* is partially obscured by gas and dust between us and the galactic center. The region around Sagittarius A* is chaotic and energetic. There are dense clusters of stars, clouds of gas heated to millions of degrees, magnetic fields that accelerate particles to near-light speeds. Occasionally, a star or gas cloud ventures too close to the black hole and is torn apart by tidal forces, its matter forming a glowing accretion disk as it spirals inward toward the event horizon. Almost all large galaxies have supermassive black holes at their centers. These cosmic anchors help shape the evolution of their galaxies, influencing how gas flows, how stars form, and how the galaxy grows over billions of years. They're not just passive features, they're active participants in galactic evolution. Yet despite its enormous mass, Sagittarius A* is remarkably quiet compared to other galactic black holes. Some galaxies have active galactic nuclei, where material falling into the central black hole releases enormous amounts of energy, sometimes outshining the entire rest of the galaxy. Our galactic center is currently in a quiescent phase, accumulating matter slowly, occasionally flaring up when something substantial falls in, but mostly just sitting there, holding the inner galaxy in its gravitational grip, 26,000 light-years away at this very moment. There is a region of space-time so warped that our ordinary understanding of physics breaks down completely, a place where time and space behave in ways that seem impossible, a place where the extreme predictions of Einstein's equations become everyday reality. And it's been there, at the center of our galaxy, for billions of years, long before our sun formed, long before Earth existed, long before life began. Our galaxy is not static. It's rotating, slowly and majestically, like a vast cosmic carousel. But this rotation is strange. Unlike anything we experience in our everyday lives, our solar system orbits the galactic center at a speed of about 220 kilometers per second. That's nearly 800,000 kilometers per hour, fast enough to circle Earth's equator in 2.5 minutes. Yet at this incredible speed, it takes approximately 250 million years for us to complete one orbit around the galaxy. Think about that timescale. 250 million years ago, dinosaurs had not yet evolved. The continents were arranged differently. Pangaea, the supercontinent, was just beginning to form. Since then, the solar system has traveled roughly halfway around the galaxy, the last time we were at this point in our galactic orbit. The Permian period had just ended with the largest mass extinction in Earth's history. When we complete this orbit and return to this same point again, Earth will be unrecognizably different. Perhaps humans will have evolved into something else. Perhaps we'll have spread to other stars. Perhaps we'll be extinct, and some other species will be the inheritors of Earth. This is a galactic year, the time it takes our sun to orbit once around the Milky Way. In the sun's lifetime of about 10 billion years, it will complete perhaps 40 galactic orbits. Our sun is currently about halfway through its life, having completed roughly 18 to 20 orbits since it formed. But here's where galactic rotation becomes truly strange. Different parts of the galaxy rotate at different speeds, but not in the way you might expect if the galaxy were a solid object. Like a wheel, the outer parts would rotate faster than the inner parts, just as the rim of a spinning wheel moves faster than points closer to the hub. But the galaxy isn't a solid object, it's held together by gravity. And the rotation follows different rules. In our solar system, planets farther from the sun orbit more slowly. This is because of how gravity decreases with distance. Neptune, in the outer reaches, crawls along its orbit, while Mercury, close to the sun, races around much faster. But in the galaxy, something strange happens. Stars in the outer regions orbit at roughly the same speed as stars closer to the center, rather than orbiting more slowly as we would expect. This is called a flat rotation curve, and it's one of the key pieces of evidence for dark matter. For the outer stars to orbit as fast as they do, there must be much more mass in the galaxy than we can see, an invisible mass that extends far beyond the visible disk, providing the extra gravity needed to keep those outer stars moving so quickly. This is dark matter, making up about 85% of the galaxy's total mass. The Milky Way rotates in a state of differential rotation. The spiral arms are density waves moving through the disk at a different rate than the stars themselves. Stars drift into the arms, slow down slightly, and then drift out again, continuing their individual orbits. The arms persist even as individual stars flow through them, like a wave on the ocean that maintains its form even as the water particles move in more complex patterns. This cosmic dance has been going on for over 10 billion years. And it will continue for billions more until the galaxy's inevitable collision with Andromeda alters everything. Let's zoom back in now. Finding our place within this vast spiral structure, we are located about 26,000 light-years from the galactic center, roughly halfway out to the edge of the visible disk. This is the galactic suburbs, not too crowded, not too sparse, a comfortable middle distance. Our position is, in many ways, fortunate. Closer to the galactic center, the density of stars is much higher and dangerous events are more common. Supernovae explode more frequently. Stars pass closer to each other, potentially disrupting planetary systems. The radiation environment is harsher, farther out, toward the edge. Stars are sparser, and heavy elements, the metals and other materials needed to form rocky planets, are less abundant. The outer regions of the galaxy are poorer in the ingredients needed for planets like Earth and Rhode, and potentially for life. But here, in the middle distance, conditions are relatively calm and stable. We're far enough from the chaotic center, but still within a region rich enough in heavy elements. Our orbit around the galaxy is nearly circular, which means we don't plunge in toward dangerous regions or venture too far into the sparse outskirts. We stay in what's called the galactic habitable zone. This isn't just coincidence. The fact that we find ourselves here, contemplating our place in the cosmos, is likely related to the fact that this region is conducive to stable, long-lived planetary systems and the emergence of complex life. From our vantage point on Earth, when we look up at the night sky, we're looking at our galaxy from within. The misty band of light that stretches across the darkest skies, the Milky Way, for which our galaxy is named as our edge-on view of the galactic disk. We're looking through the thickness of the disk, seeing millions of stars too distant and too dim to resolve individually. Their combined light creating that luminous river across the heavens. Ancient cultures around the world looked at this band of light and created stories. To the Greeks, it was milk spilled by the goddess Hera. To the Norse, it was a path to the realm of the gods. To many Native American cultures, it was a road of spirits. Chinese astronomers called it the Silver River. The ancient Egyptians saw it as a celestial Nile. All these stories were attempts to explain the same phenomenon, our view of our own galaxy from inside it. A cross-section of the cosmic structure we call home. The Milky Way defines our cosmic neighborhood. Everything we've discussed so far, from Earth to the Moon, through the solar system, past nearby stars. Across the Orion spiral of it exists within this one galaxy. These 400 billion stars, this rotating disk of matter 100,000 light-years across. This is our island universe. For most of human history, we didn't even know our galaxy was a galaxy, a distinct structure, separate from other such structures. We thought the Milky Way was simply the universe itself, and all the stars we could see were part of one continuous realm. It wasn't until the 1920s that astronomer Edwin Hubble proved that certain fuzzy patches of light in our sky were actually other galaxies, entire collections of billions of stars, far beyond the confines of the Milky Way. This revelation expanded our understanding of the universe's scale by an almost incomprehensible factor, and this brings us to the next stage of our journey. Because the Milky Way, for all its grandeur, for all its 400 billion stars and 100,000 light-year span, is just one galaxy among countless others. As we prepare to venture beyond our galaxy, into the darkness of intergalactic space, take a moment to absorb everything we've covered. Feel yourself floating above the galactic disk, looking down at those spiral arms, that glowing central bulge, those 400 billion points of light. each one a sun, many with their own planets, their own stories. This is our home galaxy, the Milky Way, and we're about to discover that it's surrounded by neighbors. Part of a community of galaxies that itself is part of larger structures still. The universe continues to expand before us. Layer upon layer, scale upon scale. Rest for a moment. Breathe slowly. Let the scale of the galaxy settle into your awareness soon. We'll go even further. ... Asterisk. Now we venture into intergalactic space, the vast darkness between galaxies. And here, 2.5 million light-years from the Milky Way, we encounter our nearest large galactic neighbor, Andromeda, also known as M31 or NGC 224. The Andromeda Galaxy is visible to the naked eye from Earth on dark, clear nights. It appears as a faint smudge of light in the constellation Andromeda, a small fuzzy patch that ancient astronomers called a nebula, not knowing they were looking at an entirely separate galaxy containing 1 trillion stars. 1 trillion stars. That's more than twice the number in the Milky Way. Andromeda is the largest galaxy in our local group, a giant spiral galaxy measuring approximately 220,000 light-years in diameter, more than twice the diameter of the Milky Way. If you could see Andromeda's full extent with your naked eyes, it would appear about 6 times larger than the full moon in our sky, spanning over 3 degrees of arc. But most of the galaxy is too faint to see without telescopes, so we perceive only its bright central core, 2.5 million light-years. The light you see when you look at Andromeda left that galaxy 2.5 million years ago. At that time, on Earth, our ancestors were early hominids Australopithecus, just beginning to use simple stone tools. They had not yet discovered fire. They could not speak in complex language. The genus Homo had not yet evolved. The light you see from Andromeda has been traveling through space for all that time, crossing the intergalactic void at 300,000 kilometers per second, finally arriving at your eye after a journey spanning most of human evolution. Andromeda is a spiral galaxy like the Milky Way, but it's structured somewhat differently. It has a larger, more luminous core, and its spiral arms are less defined than ours. It also has a more complex history. Astronomers have found evidence that Andromeda has cannibalized several smaller galaxies in the past, absorbing them and incorporating their stars into its own structure. The galaxy is surrounded by about 14 known dwarf satellite galaxies, smaller companion galaxies that orbit around it, held by its enormous gravitational pull. The most prominent of these are M32 and M110, both elliptical dwarf galaxies that can be seen in the same telescopic field of view as Andromeda itself. Like the Milky Way, Andromeda has a supermassive black hole at its center, but this one is much larger, containing an estimated 100 to 200 million solar masses, roughly 50 times more massive than Sagittarius A*. Andromeda is moving through space, and crucially, it's moving toward us, despite the expansion of the universe, which causes distant galaxies to recede from us. Andromeda is approaching the Milky Way at about 110 kilometers per second. This is because gravity, at relatively close distances, overcomes the cosmic expansion. The Milky Way and Andromeda are gravitationally bound to each other, slowly falling together through space, and this brings us to one of the most dramatic events in our cosmic future. In approximately 4 billion years, the Andromeda Galaxy and the Milky Way will collide. Let that image form in your mind. 2 vast spiral galaxies, each containing hundreds of billions of stars, slowly falling toward each other over billions of years, gradually accelerating as gravity pulls them together, until finally they interpenetrate, their spiral structures disrupted, their stars mingling in a chaotic cosmic dance. But understand this, when we say the galaxies will collide, we don't mean that stars will crash into each other. Space is so vast, and stars are so small relative to the distances between them, that the odds of any two stars actually colliding during this galactic merger are almost zero. Instead, what will happen is a gravitational ballet on the grandest scale. The two galaxies will pass through each other, their mutual gravity distorting their shapes, pulling out long tidal tails of stars that stream away from the merger site. They'll separate, slow down, reverse course, and fall together again. This process will repeat, each pass further disrupting the original spiral structures, until eventually, perhaps after several such passes, the two galaxies merge completely into a single elliptical galaxy. Astronomers have already given this future merged galaxy a name: Milkomeda or Milkdromeda. During this merger, the rate of star formation will increase dramatically as clouds of gas collide and compress. The night sky will be filled with brilliant new stars and the colorful nebulae where stars are being born. There may be periods when the sky blazes with supernova as massive stars rapidly exhaust their fuel and explode, if Earth still exists at that time and if anyone is still here to see it. The night sky will be spectacular. Andromeda will grow larger and larger over millions of years, eventually filling a huge portion of the sky. The merger itself will play out over hundreds of millions of years, a slow-motion collision visible in real time, transforming the appearance of the heavens. The Sun, if it still exists, will be flung into a new orbit within the merged galaxy, possibly ending up much closer to the new galactic core, or perhaps being tossed far out into the halo. But the Sun itself and Earth, if we're lucky, will likely survive unscathed, because the distances between stars are so enormous that direct collisions are extraordinarily unlikely by the time this collision occurs. However, Earth may already be uninhabitable for other reasons. The Sun is gradually warming as it ages, and in about 1 billion years, Earth's oceans may evaporate, making the planet too hot for life as we know it. So we probably won't be here to witness the Great Collision. At least not from Earth, but perhaps if we've spread to other stars. Our descendants will watch from a safe distance as their two home galaxies merge, creating one of the most spectacular astronomical events visible anywhere in the universe. Asterisk, the Milky Way and Andromeda are not alone. They're part of a gravitationally bound collection of galaxies called the local group. The local group contains at least 80 galaxies. The exact number is uncertain because some very faint dwarf galaxies are still being discovered spread across a region roughly 10 million light-years in diameter. But let that distance sink in for a moment. 10 million light-years. We've expanded our scale yet again. The distance from one side of the Milky Way to the other 100,000 light-years is now just 1% of the size of the local group. The local group is dominated by 3 large spiral galaxies: the Milky Way, Andromeda, and the Triangulum galaxy M33. Triangulum is the third largest member, containing perhaps 40 billion stars and located about 3 million light-years from us. It may be a satellite of Andromeda, gravitationally bound to it, and it will likely be incorporated into the Milky Way-Andromeda merger. All the other members of the local group are smaller dwarf galaxies of various types. Some are dwarf spiral galaxies, miniature versions of their larger cousins. Others are dwarf elliptical galaxies, diffuse collections of stars with no particular structure. Still others are dwarf irregular galaxies, shapeless clouds of stars and gas, the Large and Small Magellanic Clouds, visible in the southern hemisphere sky, are the most prominent dwarf satellites of the Milky Way. They're irregular dwarf galaxies, each containing a few billion stars caught in orbit around our galaxy. Eventually, in a few billion years, they'll likely be absorbed completely into the Milky Way. Other notable local group members include the Leo, the first group of dwarf galaxies, barely visible and incredibly faint; The sculptor dwarf. One of the first dwarf spheroidal galaxies discovered. The Fernax dwarf, which contains 6 globular clusters unusual for such a small galaxy. These dwarf galaxies are fossil remnants of the early universe, galaxies that never grew large. Some of them contain very little gas, having had most of their star formation in the distant past. Others are still forming stars today, though at a much slower rate than larger galaxies. Many of these dwarfs are incredibly difficult to detect. They're so faint and diffuse that they barely stand out against the background of distant stars. Astronomers discover new members of the local group occasionally. Finding these ultra-faint dwarfs hiding in the glare of more prominent objects or in previously unsurveyed regions of the sky. The local group is our cosmic neighborhood. A small cluster of galaxies bound together by gravity, floating through space as a unit. It's not an unusually large or dense group hits, fairly typical of galaxy groups throughout the universe. But it's our home, the collection of galaxies within which the Milky Way resides. Beyond the local group, space opens up into vast voids punctuated by other galaxy groups and clusters, structures on an even larger scale. In 2014, astronomers published a groundbreaking map of galaxy motions within our region of the universe. By carefully measuring how galaxies move through space, they were able to trace the flow of cosmic matter, revealing the underlying structure of gravitational attraction that shapes the universe on its largest scales. What they discovered was breathtaking. The Virgo supercluster isn't a distinct, isolated structure at all. It's part of an even larger supercluster structure, so vast that it defies easy comprehension. They named it Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is approximately 520 million light-years in diameter and contains the mass of about 100,000 trillion suns, distributed among roughly 100,000 galaxies. Let's pause and absorb that scale. 520 million light-years. Light, traveling at 300,000 kilometers per second, takes 520 million years to cross from one side of Laniakea to the other. When light left the far side of Laniakea and began traveling toward us, life on Earth was very different. Complex animals had just begun to evolve in Earth's oceans. The Cambrian explosion, that remarkable period when most major animal groups first appeared, was just beginning. The light that reaches us now from the far edge of Laniakea has been traveling since before fish existed, before plants colonized land, before dinosaurs, before mammals. Before humans, Laniakea is defined not by any visible boundary, but by the pattern of galaxy motions within it. All the galaxies in Laniakea are flowing toward a single gravitational center, a region of unusually high mass, concentration called the Great ATTRA. CTOR, the structure of Laniakea, is revealed through these motions. Galaxies flow along cosmic superhighways, following the gravitational contours of the large-scale structure. These flows converge on basin attractors regions of higher density that act like gravitational sinks. Drawing in surrounding matter, Laniakea contains several major components. The Virgo supercluster, which includes our local group, forms one arm of the structure. The Hydrocentaurus supercluster forms another major concentration. The Pavoindus supercluster represents another component. And at the core, near the border between Lanaka and the neighboring Perseus Pisces supercluster, lies the Great ATTRA-CTOR, our cosmic address. Then, read something like this: Earth Solar System, Orion Spur, Milky Way Galaxy, Local Group, Virgo, Supercluster, Laniakea Supercluster. Each level of this address represents a structure orders of magnitude larger than the one before it. And yet, even Laniakea isn't the full story. Because Laniakea itself is being pulled toward an even more massive structure, the Shapley supercluster, which lies beyond Laniakea's boundary. The universe, it seems, is structured on scales beyond scales, each new level of organization revealing yet larger patterns, near the core of Laniakea, obscured from our direct view by the plane of the Milky Way, lies one of the most mysterious structures in our region of the universe, the Great ATTR ACTOR. The Great Attractor is a gravitational anomaly, a region where the mass density is much higher than average. It's pulling our local group, along with thousands of other galaxies, toward it at a speed of several hundred kilometers per second. But here's the strange part. We can't see it directly. The Great Attractor lies in the zone of avoidance, a region of the sky obscured by the disk of our own galaxy. The dust and stars of the Milky Way block our view in that direction, making it impossible to observe distant structures with optical telescopes. So how do we know it's there? We know because of the motion of galaxies. By mapping how galaxies move, astronomers can infer where large concentrations of mass must be located, even if they can't see them directly. It's like watching leaves on a pond being drawn toward a drain. You can infer the drain's location by observing the flow pattern. Even if you can't see the drain itself, what we've been able to piece together through observations at other wavelengths radio, infrared and X-rays, that the Great Attractor region contains several massive galaxy clusters, including the Norma cluster, located about 220 million light-years away. But the story is even more complex. The Great Attractor itself isn't the ultimate source of motion in our region. It too is being pulled toward something even more massive, the Shapley supercluster, an enormous concentration of galaxies about 650 million light-years away, containing over 8,000 galaxies. The Shapley supercluster is one of the most massive structures known in the observable universe, and its gravitational influence extends across vast regions of space. We, along with the Great Attractor, along with Laniakea entire, are all being drawn in its direction. This is the nature of cosmic structure. There's always something larger, always a greater context. Galaxies are drawn into groups. Groups fall into clusters. Clusters are organized into superclusters. And superclusters are pulled toward even greater mass concentrations. But even this isn't the full picture of large-scale structure, because between these dense regions lie vast voids, immense volumes of nearly empty space. And the arrangement of these dense regions and voids forms a pattern that only becomes visible when we zoom out even further. Now we pull back to truly cosmic scales, expanding our view until we can see billions of light-years in any direction. From this perspective, the universe reveals its grandest architecture, the cosmic web. The cosmic web is the large-scale structure of the universe, a vast three-dimensional network of matter that spans the entire observable cosmos. It's called a web because, when mapped, it genuinely resembles a spider's web, a network of filaments connecting dense nodes. With vast, empty spaces between them, this structure consists of four main components: filaments. These are vast, thread-like structures of galaxies and dark matter, stretching for hundreds of millions of light-years through space. They're the densest parts of the cosmic web, containing most of the universe's galaxies. Filaments can be incredibly long, some stretch for over 1 billion light-years. They form the threads of the cosmic web. Nodes, where filaments intersect. You find nodes, massive galaxy clusters, and superclusters, like the Virgo cluster and the Shapley supercluster. These are the densest regions of the universe, containing thousands of galaxies concentrated in relatively small volumes of space. They're like the junctions where multiple threads of a web come together. Walls, sometimes filaments, spread out into sheet-like structures called walls. These are two-dimensional surfaces of galaxies, marking the boundaries between voids. The most famous example is the Sloan Great Wall, a vast structure over 1 billion light-years long, containing tens of thousands of galaxies arranged in an enormous sheet. Voids between the filaments. walls, and nodes lie the void's vast, nearly empty regions of space, typically 100 million to 300 million light-years across. These voids contain very few galaxies, sometimes none at all. They're the empty spaces between the threads of the web. The cosmic web isn't random. It formed through the action of gravity over billions of years, amplifying tiny density variations that existed in the very early universe, in the moments after the Big Bang. Matter was spread almost perfectly evenly through space. But almost is the key word. There were tiny variations in densities. Some regions were slightly denser than others. These variations were incredibly small. Differences of only 1 part in 100,000. But gravity amplifies density differences. Regions that were slightly denser had slightly more gravity, which attracted more matter, making them denser still. Over millions and billions of years, this process caused matter to flow along gravitational contours, gradually building up the filaments and nodes we see today, while draining the regions that became voids. The result is the cosmic web, a structure that fills the entire universe, at least the part we can observe from our position within the Laniakea supercluster. We're located within one of the filaments of this vast web. If you could somehow see the universe from outside, you would see our entire supercluster as just one bright knot in an enormous network of light. With dark voids stretching between the bright regions, the cosmic web is mind-boggling in its scale. Yet it's also remarkably delicate in its structure. Despite containing all the galaxies in the universe, the filaments and walls are actually quite thin relative to their length. The universe's matter is concentrated into these structures, leaving the voids profoundly empty. Let's focus on some specific structures within the cosmic web to give you a sense of just how large these features can be. The Sloan Great Wall, discovered in 2003. This is one of the largest known structures in the universe. It's a vast wall of galaxies stretching for about 1.37 billion light-years through space. This structure is so large that light takes over 1 billion years to cross from one end to the other. It contains tens of thousands of galaxies, all arranged in a sheet-like formation. If you could view it from the side, it would appear as a vast, flat concentration of galaxies, like a cosmic membrane stretching through the darkness. The CFA-2 Great Wall, also known as the Coma Wall. This structure was one of the first Great Walls discovered, found in the 1980s during the CFA Redshift survey. It stretches about 500 million light-years across the sky and contains the Coma Cluster, one of the richest galaxy clusters known, the Hercules Corona, Oculus Great Wall. This might be the largest structure ever discovered in the universe, detected through the distribution of gamma-ray bursts. It spans approximately 10 billion light-years, more than 10% of the diameter of the observable universe. Its existence is somewhat controversial and is still being studied, but if confirmed, it represents a structure so large that it challenges our understanding of how the universe should be organized. These walls mark the boundaries between voids, and the voids themselves are equally remarkable for their emptiness. The Boats Void, discovered in 1981. This is one of the largest known voids in the universe, measuring approximately 330 million light-years in diameter. It's sometimes called the Great Nothing. Within this vast volume, there are only about 60 galaxies, where you might expect to find around 2,000 based on the average density of the universe. Standing in the center of the Boats Void, the nearest galaxy would be tens of millions of light-years away in every direction. The night sky would contain almost no visible galaxies at all, just darkness, the Eridanus supervoid. This void might be responsible for a mysterious feature in the cosmic microwave. Background radiation, a cold spot that's colder than expected. The void is about 1 billion light-years across, and the deficit of matter within it might be affecting the temperature of the ancient radiation passing through it. Voids are not completely empty. They contain the intergalactic medium extremely diffuse gas, mostly hydrogen and helium. They also contain dark matter, that invisible substance that makes up most of the universe's mass. But they contain very few galaxies, and the galaxies they do contain are typically small. Dim dwarf galaxies that formed from the minimal matter available in these regions. The existence of voids and walls tells us something profound about the universe. The distribution of matter isn't random, it's highly structured, organized by gravity into a pattern that fills space. This cosmic web is a fossil, in a sense, preserving information about conditions in the very early universe. The pattern of filaments and voids we see today is an enlarged version of the pattern of density variations that existed when the universe was only 380,000 years old, those tiny ripples in the density of matter that have been amplified by billions of years of gravitational evolution. When astronomers map the cosmic web, they're seeing the consequence of quantum fluctuations in the incredibly early universe. Tiny variations in energy density that existed in the first fraction of a second after the Big Bang, now expanded and amplified to become structures billions of light years across. It's one of the most beautiful examples of how the very small and the very large are connected in cosmology, how events at the quantum scale in the first moments of time can shape the largest structures we can observe as we prepare to expand our view even further. To encompass the entire observable universe, take a moment to visualize this cosmic web. Imagine those vast filaments of galaxies stretching for billions of light years. Imagine the great walls, sheet-like structures containing thousands of galaxies. Imagine the voids, those bubbles of emptiness where almost nothing exists except darkness and diffuse gas, and realize that all of this, every galaxy, every supercluster, every wall and void we've discussed, exists within just a portion of the observable universe. There's more. So much more. Let your mind rest for a moment. We've traveled from Earth to structures billions of light years across. We've seen how the universe organizes itself on its largest scales, forming a web of light and darkness that fills space as far as we can see. Soon, we'll discuss the limits of what we can observe and what might lie beyond. Now we come to the boundaries of observation, the edge of what we can possibly see. The observable universe, the region of space from which light has had time to reach us since the Big Bang, is approximately 93 billion light-years in diameter. You might notice something strange about that number. If the universe is 13.8 billion years old, shouldn't we only be able to see 13.8 billion light-years in any direction? Shouldn't the observable universe be about 28 billion light-years across, not 93 billion? This is where the expansion of the universe comes into play. The light we see from the most distant galaxies was emitted billions of years ago, when those galaxies were much closer to us. But in the time that light has been traveling toward us, space itself has been expanding, stretching the fabric of the cosmos, carrying those galaxies farther away. So when we observe a galaxy whose light has been traveling for 13 billion years, that galaxy is no longer 13 billion light-years away. It's now about 46 billion light-years away, carried to that distance by the expansion of space during the time its light was in transit. This means the observable universe is much larger than you might expect. A sphere centered on us, extending about 46.5 billion light-years in every direction, giving a total diameter of 93 billion light-years. This is not the size of the entire universe. It's only the size of the region we can observe. The actual universe is likely much larger, possibly infinite. But the observable universe represents the limit of what we can possibly see. Even in principle, even with perfect instruments, within this observable sphere, we estimate there are approximately 2 trillion galaxies. 2 trillion. Each containing millions, billions, or even trillions of stars, each potentially harboring countless planets. The total number of stars in the observable universe is estimated to be around 1 septillion. That's 1 followed by 24 zeros. Written out, unlimited stars. More stars than grains of sand on all the beaches on Earth, more stars than seconds have elapsed since the Big Bang. More stars than any human could count in 1,000 lifetimes, and every one of those stars is a sun, potentially with its own system of planets, its own story of formation and evolution, its own place in the cosmic web. The observable universe contains all of the Sol, the galaxies, all the superclusters, all the filaments and voids of the cosmic web of it contained within that 93 billion light-year sphere, at the center of which, from our perspective, sits Earth. But understand this, we're not actually at the center of anything. Every point in the universe sees itself as the center of the observable universe. An observer in a galaxy 10 billion light-years from us would see their own observable universe, a different sphere of the same size, centered on them. Some of what they see would overlap with what we see, but much of their observable universe would be forever invisible to us, lying beyond our cosmic horizon. The boundary of the observable universe is often called the cosmic horizon or the particle horizon. It's fundamentally different from any other boundary we've discussed. It's not a physical edge. There's no wall, no barrier, no sign that says end of the universe. It's simply the limit of observation, a boundary created by the finite speed of light and the finite age of the universe. Light from regions beyond the cosmic horizon has not had time to reach us yet. The universe hasn't been around long enough for that light to complete the journey. In a sense, these regions are not just invisible, they're unobservable in principle. At least for now, and because the universe is expanding, this situation is actually getting worse, not better. You might think that as time passes, we'd be able to see farther and farther, as light from more distant regions finally reaches us. And in a non-expanding universe, that would be true. But our universe is not only expanding, its expansion is accelerating. Driven by dark energy, the expansion rate is increasing over time. This means that galaxies beyond a certain distance are receding from us faster than light can travel through the expanding space between us. These galaxies are not breaking the cosmic speed limit. Nothing can move through space faster than light. But space itself can expand faster than light, carrying galaxies with it. The result is that there are regions of the universe that are receding from us so quickly that light emitted from them now will never reach us, no matter how long we wait. In fact, galaxies we can currently observe are gradually disappearing from view as they're carried beyond this boundary by the accelerating expansion in the far future. Trillions of years from now, the observable universe will contain far fewer galaxies than it does today. Our descendants, if they exist, will look out into a much emptier cosmos, with only the gravitationally bound local group remaining visible. All other galaxies will have been carried beyond the cosmic horizon, their light redshifted into undetectability. But for now, we can still see a rich tapestry of galaxies spread across the observable universe, a vast sample of cosmic structure that allows us to study the universe's history and composition. Let's focus on the most distant galaxies we can observe. Those objects at the very edge of our cosmic horizon. The farthest galaxies we've detected are seen as they existed, just a few 100 million years after the Big Bang. We're seeing them not as they are now, but as they were over 13 billion years ago. When the universe was young and very different from today, these early galaxies are small and irregular compared to modern galaxies like the Milky Way. They're vigorously forming stars, converting their gas into new suns at rates far higher than contemporary galaxies. They're building blocks, small galaxies that will eventually merge together to form the larger galaxies we see in the more recent universe. One of the most distant confirmed galaxies is GNZ 11, observed by the Hubble Space Telescope. The light we see from this galaxy was emitted just 400 million years after the Big Bang, when the universe was only 3% of its current age. We're seeing this galaxy as it existed 13.4 billion years ago. During the time that galaxy's light has been traveling toward us, the universe has expanded tremendously. GNC 11 is now estimated to be about 32 billion light-years away from us. Carried to that distance by cosmic expansion, the James Webb Space Telescope, launched in 2021, has pushed even further, detecting galaxies that existed just 200 million years after the Big Bang. These observations are revolutionizing our understanding of how quickly galaxies formed in the early universe. These distant galaxies appear red in our observations. Their light stretched to longer wavelengths by the expansion of the universe. This effect is called redshift, and it's one of the key tools astronomers use to measure cosmic distances. Looking at these distant galaxies is like looking at cosmic archaeology. We're seeing the early chapters of the universe's story, the era when the first stars and galaxies were forming, when the universe was transitioning from a dark age, after the initial fireball of the Big Bang had cooled, but before stars had formed, into an age of light, as stellar furnaces ignited throughout space. Let's take a moment to understand redshift, because it's fundamental to how we measure the universe's scale and its expansion. When a light source moves away from you, the wavelength of its light gets stretched, shifting toward the red end of the spectrum. This is similar to the Doppler effect for sound, how an ambulance siren sounds lower in pitch as it moves away from you. But cosmological redshift is slightly different. It's not caused by galaxies moving through space, but by space itself expanding, stretching the wavelength of light as it travels through expanding space. Imagine drawing dots on a balloon, then inflating it. As the balloon expands, the dots move apart. But they're not moving across the surface itself is expanding between them. Similarly, as the universe expands, the space between galaxies stretches, and light waves traveling through that space get stretched along with it. Astronomers measure redshift as a number, denoted by Z. Nearby galaxies have small redshifts, typically Z less than 0.1. Distant galaxies have larger redshifts. The most distant galaxies observed have redshifts of 10 or more, meaning their light has been stretched to wavelengths 10 times longer than when it was emitted. The relationship between redshift and distance tells us about the expansion history of the universe. By measuring how redshift changes with distance, astronomers discovered one of the most profound facts about our cosmos. The universe's expansion is accelerating. This discovery, made in the late 1990s, was completely unexpected. Astronomers expected that gravity would be slowing down the expansion, causing it to decelerate over time. Instead, they found that distant supernovae were farther away than expected, indicating that the expansion has been speeding up. This acceleration is attributed to dark energy, a mysterious property of space itself that acts like a repulsive force, pushing space apart. Dark energy makes up approximately 68% of the total energy content of the universe. Yet we have no idea what it actually is. It's one of the greatest mysteries in modern physics, the expansion of the universe. And its acceleration fundamentally shapes our observations of the cosmos. It's why the observable universe is larger than its age might suggest. It's why distant galaxies appear red. And it's why there's a cosmic horizon beyond which we cannot see. There's one more thing we can observe at the edge of our cosmic horizon. And it's perhaps the most remarkable observation of all: the cosmic microwave background radiation, or CMB. The CMB is the oldest light in the universe. It was emitted when the universe was only 380,000 years old, during an era called recombination. When the universe had finally cooled enough for atoms to form before recombination, the universe was a hot, dense plasma soup of electrons, protons, and photons all interacting with each other. This plasma was opaque to light. Photons couldn't travel far before being scattered by electrons. The universe was like the inside of a star-hot, bright, and completely opaque. But as the universe expanded and cooled, eventually it reached a temperature where electrons and protons could combine to form neutral hydrogen atoms. When this happened, photons were suddenly free to travel through space unimpeded. The universe became transparent. Those photons have been traveling through space ever since, for over 13.7 billion years. As they've traveled, they've been stretched by the expansion of the universe, their wavelength increasing from visible light to infrared and finally to microwaves. Today, we detect them as a faint glow of microwave radiation coming from every direction in the sky. The CMB appears almost perfectly uniform, with a temperature of about 2.7 degrees above absolute zero, 2.725 Kelvin, to be precise. But when you look closely, there are tiny variations in temperature differences of only about 1 part in 100,000. These tiny ripples in temperature represent density variations in the early universe. The seeds that would eventually grow into all the structure we see today: galaxies, clusters, superclusters, the entire cosmic web. The cosmic microwave background is a photograph of the infant universe, a snapshot taken when the cosmos was less than 1% of its current age. It's the most distant thing we can observe, coming from a distance of about 46 billion light-years, the edge of our observable universe. Beyond the CMB, we cannot see. The universe was opaque before recombination, and so no light from earlier times can reach us. The CMB forms a kind of wall, a luminous sphere surrounding us in every direction, beyond which direct observation is impossible. Yet studying this ancient light has revealed an enormous amount about the universe. By analyzing the pattern of temperature variations in the CMB, cosmologists have been able to determine the age of the universe, its geometry, its composition, and the parameters that govern its expansion. The CMB is, in many ways, our Rosetta Stone for understanding the cosmos. When you look at images of the cosmic microwave background, you're seeing the universe as it was 13.7 billion years ago. You're seeing the afterglow of the Big Bang itself, the echo of creation still reverberating through space. This is the edge of observation. Beyond this, we enter the realm of inference and speculation, trying to understand what lies beyond our cosmic horizon. And that's where our journey takes us next. Rest now. Feel the scale of what we've discussed. 93 billion light-years, 2 trillion galaxies, 1 septillion stars, and all of it visible to us because of light that has been traveling for billions of years to reach our eyes. Soon we'll ask, what lies beyond? And how big might the universe truly be? We've reached the edge of what we can observe. But our journey isn't quite over, because the universe doesn't end at our cosmic horizon. That boundary exists only from our perspective. It's a limit on what we can see, not a limit on what exists beyond the observable universe. Space continues. There are more galaxies, more stars, more planet structures and objects that are forever beyond our ability to observe because their light has not had time, and never will have time, to reach us. So how big is the universe beyond what we can see? The honest answer is, we don't know. And we may never know for certain, but we can make some educated inferences based on what we do observe within our cosmic horizon. The observable universe appears to be remarkably uniform at large scales. When you look in any direction, after accounting for local structures like our galaxy and nearby clusters, the universe looks statistically the same. The density of galaxies, the distribution of matter, the properties of space itself appear uniform. No matter which direction we look, This observation is called the cosmological principle, and it suggests that there's nothing special about our location in the universe. If the universe looks the same in all directions from our vantage point, and if we're not in a special location, then it should look similarly uniform from any other location as well. This implies that beyond our cosmic horizon, the universe probably continues with the same properties, the same structures, the same distribution of galaxies and voids and superclusters that we see within our observable region. But how far does it extend? There are several possibilities, each with profound implications. First, the universe might be finite but unbounded. Imagine the surface of a sphere. It's finite in area, but it has no edge. If you travel in any direction on a sphere's surface, you never reach a boundary. You just eventually return to your starting point. The universe could be curved back on itself in a similar way, but in 3 dimensions instead of 2. This is called a closed universe. In a closed universe, if you could somehow travel far enough in a straight line, you would eventually return to your starting point, having circumnavigated the entire cosmos. The universe would have a finite volume, though you could never reach an edge because there is no edge. Second, the universe might be flat and infinite. This is what current observations suggest is most likely. The geometry of space, as measured by observations of the cosmic microwave background, appears to be very close to flat, neither curved like a sphere nor curved like a saddle. If the universe is exactly flat, and if it follows the cosmological principle everywhere, then it extends infinitely in all directions. An infinite universe is a strange concept to contemplate. It would mean there's no center, no edge, just an endless expanse of space filled with galaxies and structure continuing forever. Everything that can happen, given enough space and time, would happen somewhere in an infinite universe. In fact, it would happen an infinite number of times. Third, the universe might be finite, but so large that its curvature is unmeasurable. We can only measure the geometry of space within our observable region. If the universe is curved, but the radius of that curvature is much larger than our observable universe, we wouldn't be able to detect it. The universe would appear flat to us, even though at much larger scales it curves back on itself. Current observations suggest that if the universe is curved, its radius of curvature must be at least 400 times larger than the observable universe. That would make the full universe at least 37 trillion light-years in diameter, 400 times larger than what we can observe. But these are just constraints. The actual size could be far larger still, or it could be infinite. The universe beyond our horizon remains a profound mystery, accessible only through mathematics and inference, never through direct observation. Let's explore what an infinite universe would actually mean. Infinity is not just a very large number. It's a fundamentally different category. You can't count to infinity. You can't measure infinity. You can't even properly imagine infinity. Because our minds evolved to deal with finite quantities, but mathematics handles infinity routinely. And the mathematics of cosmology suggests that an infinite universe is not only possible, but perhaps likely in an infinite universe. Everything is repeated not just once, but infinitely many times. Consider this. The number of possible configurations of matter within any finite volume is large, but it's still finite. There are only so many ways you can arrange the atoms in a region of space, the size of our observable universe. But if space extends infinitely, and if matter is distributed similarly everywhere following the cosmological principle, then every possible configuration must occur somewhere. And in infinity, it must occur infinitely many times. This leads to a startling conclusion. If the universe is infinite, there must be other regions identical to our observable universe. Not similar, identical. Exact copies down to every atom, every galaxy, every planet. Every person there would be another Earth, orbiting another sun, in another Milky Way galaxy, in another region of space. where another version of you is listening to or reading these exact words at this exact moment. In fact, in an infinite universe, there would be infinitely many such regions. Infinitely many copies of Earth, of you, of everyone who has ever lived. And there would also be infinitely many variations regions where things unfolded slightly differently, where different choices were made, where history diverged. This is not science fiction. This is a mathematical consequence of an infinite universe with finite possible configurations. The physicist Max Tegmark has calculated that in an infinite universe, following the cosmological principle, there should be an identical copy of our observable universe about 10 to the power of 29 meters away. That distance is so large it's meaningless in any practical sense. But conceptually, it's profound. Infinity is strange. Infinity contains everything that can exist, repeated endlessly through space. Of course, we can never verify this. We can never observe those distant copies because they lie beyond our cosmic horizon. They will forever remain a theoretical consequence of cosmic infinity, true if the universe is infinite, but forever unobservable. Yet the very fact that infinity is possible, that our universe might have no end, no ultimate boundary, should inspire a sense of awe. We're not just in a large universe, we might be in an endless one, a cosmos that continues forever in every direction, filled with infinite galaxies, infinite stars, infinite possibilities. But there's an even more mind-bending possibility to consider. What if our universe, vast as it is not the only universe? What if it's just one bubble in an infinite foam of universes, each with its own properties, its own laws of physics, its own history? This is the multiverse hypothesis, and while it sounds like science fiction, it emerges naturally from several areas of theoretical physics. One version comes from inflationary theory, which explains how the universe expanded exponentially in the first fraction of a second after the Big Bang. According to eternal inflation theory, the inflationary process never completely stops. While inflation ended in our region of space, allowing our universe to form, it continues in other regions, spawning new bubble universes that are forever separated from our own. Each bubble universe could have different physical constants, different laws of physics, different properties. Some might have conditions suitable for galaxies and stars and planets. Others might be empty, or too dense, or too unstable for any complex structures to form. In this scenario, our observable universe is just one bubble among infinite bubbles, each one an entire universe in its own right, each forever isolated from the others by the eternally inflating space between them. Another version of the multiverse comes from quantum mechanics. In the many worlds interpretation of quantum theory, every quantum measurement causes the universe to split into multiple branches, one for each possible outcome. Each branch is equally real, constituting its own universe, where a different outcome occurred. If this interpretation is correct, and it's worth noting that it remains highly controversial. Among physicists, then, there are countless parallel universes constantly branching off from our own, each following a different path through the tree of quantum possibilities. Yet another version comes from string theory, which suggests there may be additional dimensions of space beyond the three we experience. Our universe might be a three-dimensional brain, short for membrane, floating in a higher dimensional space, with other brains, other universes existing nearby in dimensions we cannot access. These ideas are highly speculative. They emerge from mathematical theories that, while successful in describing aspects of our universe, make predictions that extend far beyond what we can test experimentally. Most scientists remain agnostic about whether the multiverse actually exists, treating it as an interesting theoretical possibility rather than established fact. But the very fact that our best theories suggest the possibility of a multiverse tells us something important. The universe we observe might not be all there is. Reality might be far larger, far stranger. far more complex than even our most ambitious observations can reveal. The multiverse, if it exists, would represent an ultimate limit on human knowledge, not just regions we cannot observe because they're too far away, but entire domains of reality that are fundamentally inaccessible to us, separated by barriers we can never cross. Let's return to questions we can address with current observations. What is the shape of the universe? And what will happen to it in the far future? The shape of space, its geometry, is determined by the total density of matter and energy it contains. According to Einstein's general theory of relativity, if the universe contains more than a certain critical density, it's positively curved, like the surface of a sphere. This is called a closed universe, and in this scenario, the universe is finite, though unbounded. Gravity would eventually halt the expansion and cause the universe to recollapse in a big crunch. If the universe contains less than the critical density, it's negatively curved, like a saddle shape. This is called an open universe, and it would expand forever, gradually cooling and emptying as galaxies recede from each other. If the universe contains exactly the critical density, it's flat, neither positively nor negatively curved. Current observations, particularly measurements of the cosmic microwave background by satellites like WMAP and Planck, suggest that the universe is very close to flat. Within a margin of error of less than 1%, a flat universe will also expand forever. But the expansion will gradually slow down, asymptotically approaching a finite rate. However, there's a complication: dark energy. That mysterious component, making up 68% of the universe's energy budget, acts as a repulsive force, accelerating the expansion. With dark energy dominating, the universe's fate depends on the properties of dark energy itself. If dark energy remains constant, as in the simplest models, where it's just a property of empty space itself, called the cosmological constant, then the universe will continue expanding forever. With the expansion accelerating, this leads to a scenario called the Big Freeze or heat death. In the far future, trillions upon trillions of years from now, the accelerating expansion will have carried all but the closest, gravitationally bound galaxies beyond our cosmic horizon. The universe will become cold, dark, and empty. Stars will exhaust their fuel and die. Black holes will gradually evaporate through a quantum process called Hawking radiation. Eventually, even protons might decay, dissolving the very atoms that make up matter in the ultimate far future. Perhaps 10 to the power of 100 years from now, the universe might contain nothing but a diffuse bath of radiation spread across an ever-expanding void, with a temperature approaching absolute zero. But if dark energy changes over time, if it strengthens, then the fate could be even more dramatic. In a scenario called the Big Rip, the acceleration would increase until eventually it tears apart gravitationally bound structures. First, galaxy clusters would be ripped apart, then galaxies, then stellar systems, then planets, then molecules, atoms, even atomic nuclei. Everything would be torn apart by the exponentially accelerating expansion, until nothing remains but elementary particles in isolation. Alternatively, if dark energy decreases or becomes negative, gravity could eventually win, halting the expansion and causing the universe to collapse in a big crunch, perhaps to be reborn in another Big Bang. In an eternal cycle of expansion and collapse, we simply don't know which scenario will play out, because we don't yet understand what dark energy truly is. But regardless of the ultimate fate, we can be certain of this: the universe as we know it is temporary. The stars will not shine forever. The galaxies will not endure eternally. Everything that exists now will, in time, transform into something else or dissolve into emptiness. Yet this should not be cause for despair. Instead, it reminds us how precious and remarkable the current epoch Zizan era, when the universe is filled with structure and light, when complexity and life are possible, when conscious beings can contemplate the cosmos and wonder at its immensity. We exist in a brief window of cosmic history, between the initial fireball of creation and the eventual emptiness of the far future. In this window, the universe has organized itself into galaxies and stars and planets. On at least one of those planets, matter has organized itself into life, and life has organized itself into consciousness. And consciousness has developed the ability to observe and understand the universe it inhabits. This is no small thing. This is, perhaps, the universe becoming aware of itself. Matter contemplating matter. The cosmos asking questions about its own nature and origin. As we prepare to conclude our journey, take a moment to absorb these deep questions about the universe's extent and fate. We may never know how big the universe truly is, or what lies beyond our cosmic horizon, or whether other universes exist, or what will happen in the inconceivably distant future. But we can know this: we are part of something vast and ancient and beautiful, something that extends far beyond our immediate experience, something worthy of wonder and contemplation. Rest now. Let these vast scales settle in your mind. Infinity, multiverses. The ultimate fate of all things, these are questions that have occupied human minds since we first looked up at the stars and asked, what is all this? Where does it come from? Where's it going? Soon we'll bring our journey full circle, returning to Earth, to the human scale, and reflecting on what all this vastness means for us. Let's return now, slowly, gently, from the vast scales we've been contemplating. Back to the human scale, back to Earth, back to this moment. Here and now, we've journeyed from Earth to the Moon, a distance of 384,000 kilometers. Then outward through the solar system, past the planets, past Voyager, to the Oort cloud. 2 light-years from the Sun, we ventured into interstellar space, visiting our nearest stellar neighbors light-years away. We explored the Orion Spur, our local region of the galaxy, containing millions of stars. We zoomed out to see the entire Milky Way, 100,000 light-years across, containing 400 billion stars spiraling around a supermassive black hole. We crossed intergalactic space to Andromeda, 2.5 million light-years distant, and saw our local group of galaxies, 10 million light-years across. We expanded our view to encompass superclusters Virgo, then Laniakea structures hundreds of millions of light-years in size, part of the cosmic web that fills space. We reached the edge of observation, the boundary of our cosmic horizon, 93 billion light-years away, marked by the ancient light of the cosmic microwave background, and we contemplated what might lie beyond, an infinite universe, perhaps, or even a multiverse of countless separate universes. Now, let's reverse this journey. Let's zoom back in through all these layers of scale until we return to where we started. From the cosmic web, collapse your perspective back to Laniakea, that great supercluster of 100,000 galaxies. See it shrink in your mind's eye, becoming smaller as we zoom inward. Focus on the Virgo supercluster. Then the local group. There's Andromeda, that great spiral galaxy. And they're much smaller from this distance, says the Milky Way dot. Zoom into the Milky Way. See its spiral arms, its glowing core. Find the Orion Spur, that minor arm where our Sun resides. The galaxy shrinks around you as you move inward, until you can distinguish individual stars. There's the Sun, one star among 400 billion, unremarkable in most ways, but special to us because it's ours. Zoom into the solar system. See the planets in their orbits: Neptune, Uranus, Saturn, Jupiter, the asteroid belt, Mars, Earth, Venus, Mercury, all arranged around that central yellow star. Focus on Earth, that pale blue dot, as Carl Sagan called it. From space, it's barely visible, a tiny world in the vast darkness. But as we zoom closer, details emerge. Continents, oceans, clouds, the thin line of the atmosphere separating life from the void. And there, on the surface of this small world, is you. Right here, right now. Reading or listening to these words, contemplating the vastness of everything we've discussed. You are here, on this planet, in this solar system, in this galaxy, in this local group, in this supercluster. In this universe, you are made of atoms forged in ancient stars, particles that have journeyed through billions of years of cosmic history to come together. Briefly, as you asterisk to help put our place in time into perspective, let's compress the entire history of the universe into a single calendar year. On this cosmic calendar, the Big Bang happens at the stroke of midnight on January 1st. The universe is born in a flash of energy and begins expanding. For most of January, the universe is a hot soup of particles, gradually cooling and expanding. The first atoms form on January 10th, and the cosmic microwave background is emitted that ancient light we can still observe today. February, March, April pass. The universe continues expanding, cooling, growing darker. Gravity slowly amplifies tiny density variations. In May, the first stars ignite. The dark age ends. Galaxies begin to form. June, July, August pass. Galaxies merge and grow. The cosmic web takes shape. The universe begins to look recognizable. On September 2nd, our Milky Way galaxy forms from the collision and merger of smaller proto-galaxies through September. October, November, December, stars are born and die. Galaxies evolve. The universe continues its expansion. On September 9th, our solar system forms from a cloud of gas and dust, enriched by the debris of earlier generations of stars. September 14th, Earth forms. A ball of molten rock bombarded by asteroids and comets. September 21st, life appears on Earth. Simple single-celled organisms in the oceans. And then, nothing dramatic happens for a very long time on our calendar. Life remains simple, single-celled, gradually evolving but not producing anything we would recognize as complex. December 17th. Complex multicellular life appears. The Cambrian explosion of life begins. December 26th. Dinosaurs appear. December 30th. Dinosaurs go extinct. Mammals diversify. December 31st at 11:52 p.m., just 8 minutes before midnight modern. Humans appear. All of recorded human history occupies the last 14 seconds of the cosmic year. The pyramids were built 5 seconds ago. The Renaissance happened 1 second ago. This is our place in cosmic time. We're very, very late arrivals to the universe's story. The cosmos existed for over 13 billion years before humans appeared. Stars were born and died. Galaxies collided and merged. The universe evolved through countless changes, all before our species took its first breath. And yet, in our brief moment on the cosmic stage, we've developed the ability to understand all of this. We've deciphered the history of the universe, measured its age and size, understood the forces that govern it. We've looked backward to the Big Bang and forward to the universe's ultimate fate. This is remarkable. It's one of the most extraordinary achievements of our species, given the immense scale of the universe, given the hundreds of billions of galaxies, each containing hundreds of billions of stars, many with planets. Some of those planets surely inhabitable zones around their stars. Where is everybody? This question, posed by physicist Enrico Fermi, has come to be known as the Fermi paradox. If life can emerge from chemistry, as it did on Earth, and if the universe is as vast and old as we've described, then life should be common. Some of that life might develop intelligence, technology, the ability to communicate across interstellar distances. perhaps even to travel between stars. Given the age of the Milky Way, way over 10 billion years, there has been plenty of time for intelligent civilizations to arise, spread through the galaxy, make themselves obvious. Even traveling at a small fraction of light speed, a civilization could colonize the entire galaxy in just a few million years. A cosmic EYEBLINK. So where are they? Why do we see no evidence of alien civilizations? Why is the galaxy not filled with their radio signals, their megastructures, their presence? Many solutions have been proposed to this paradox. Perhaps life is extremely rare, requiring such a precise combination of conditions that Earth might be one of the few places where it emerged. Perhaps intelligence's rare life might be common. But the step from simple life to complex, intelligent, technological life might be extraordinarily unlikely. Perhaps civilizations destroy themselves shortly after developing advanced technology. Through war, environmental collapse, or AI gone wrong. Before they have a chance to spread through the galaxy. Perhaps interstellar travel is simply too difficult, too expensive, too slow. And civilizations remain confined to their home worlds. Perhaps we're looking in the wrong way or at the wrong time. Perhaps advanced civilizations use communication, technologies we haven't imagined yet. Or perhaps, and this is a sobering thought, we're alone. Perhaps in all the vastness we've explored tonight, in all those trillions of galaxies and septillion stars, Earth is unique, life is unique, consciousness is unique. Perhaps we're the universe's only way of knowing itself. We don't know the answer. The universe is vast enough that life could be common. Yet the distances are so great that communication or contact might be effectively impossible. We might be surrounded by life and never know it, simply because space is too large, time is too long, and signals are too faint. Or we might truly be alone, the only conscious observers in all of creation. Either possibility is profound. Either possibility should inspire both wonder and responsibility. We've completed our journey through the scales of the universe, from Earth to the cosmic horizon and beyond, contemplating distances so vast that even light takes billions of years to cross them. So, how big is our universe? The observable universe is 93 billion light-years in diameter, containing approximately 2 trillion galaxies and a septillion stars. This is what we can see, the region from which light has had time to reach us. The universe beyond our horizon is unknown. It might extend for a distance many times larger. It might be infinite, continuing forever in all directions. We may never know for certain, but what we do know is extraordinary. We know that we exist in a cosmos of breathtaking scale and complexity. We know that we're made of star stuff, atoms forged in stellar furnaces and scattered through space by exploding stars. We know that we're connected to everything in the universe through a chain of causation, stretching back to the Big Bang itself. We know that space is mostly empty. Yet what fills it, the galaxies, stars, and planets, is wondrous. We know that we live in a universe governed by mathematical laws we can understand, a cosmos that reveals its secrets to careful observation and patient thought. And perhaps most importantly, we know that we're here, now in this brief window of cosmic history, able to contemplate all of this, able to ask these questions, able to experience wonder at the immensity of existence. The universe is vast beyond comprehension. Yet here you are, a small part of it, a momentary arrangement of atoms that can think and feel and wonder. You contain within you the same atoms that once dwelt in ancient stars. You're connected to everything through the great cosmic web, through the history of matter itself. When you feel small and insignificant in the face of cosmic vastness, remember this: you're part of the universe observing itself. Through you, the cosmos has become conscious, has developed eyes to see and minds to understand. You're not separate from the universe. you're one of the ways the universe exists. The scale we've explored tonight, from human dimensions to cosmic horizons, reveals something important. Perspective is everything. Your daily concerns, your worries and fears, they matter to you and to those around you. They're real and valid. But they exist within a larger context. A context so vast that it can provide comfort, perspective, a sense of connection to something greater. When ancient humans looked up at the night sky, they saw mystery and created myths to explain it. We, with our telescopes and equations, have replaced those myths with knowledge, but the sense of wonder remains. If anything, it's deepened. The reality we've discovered is more amazing than any myth. We live in a universe that began in a cosmic fireball, 13.8 billion years ago. We live in an era when the universe is filled with structure and light. We live on a planet where matter has organized itself into life and consciousness. We're able to look out into the universe and understand what we see. This is an extraordinary time to be alive. This is an extraordinary thing to be a conscious being, able to contemplate the cosmos. So as you prepare to sleep, as you let these thoughts settle into your unconscious mind, take comfort in this. You're part of something vast and ancient and beautiful. You're connected to everything through bonds of matter and energy and history. You're home, not just on Earth, but in the universe itself, universe that is. In every direction, filled with wonders beyond counting. The universe is big, bigger than we can truly comprehend. But you're part of it, and it's part of you. Rest now. Let your breathing slow. Let your body relax completely. Let your mind drift among the galaxies, floating peacefully through the cosmic web, suspended in the vast darkness between stars. At home in the infinite expanse, the universe is singing a song that began 13.8 billion years ago and will continue for trillions of years to come. You're a note in that song, brief but essential, unique and irreplaceable. Sleep well. Dream of stars and galaxies and infinite space. Dream of the cosmos in all its glory. Dream of your place within the grandest story ever told, the story of the universe itself. And when you wake, remember, you carry the universe within you, and the universe carries you within it. You're never truly alone because you're always part of everything, connected to all that is, was, and ever will be. Good night. Rest peacefully. The universe continues its journey through time, and so do you. Together, eternally intertwined. The stars are waiting. The galaxies are turning. The cosmos is expanding. And you are here now, part of it all. Rest.